come to the discussion of the band break. Myself, Dr. Kushal Bhattacharya, is going to present the lecture on the band break. Now, let us see how the construction of the band break works. Now, the band breaks is basically consists of a flexible steel strip shown in red color, and it is mounted over a rotating brake drum. The flexible steel strip consists of a friction lining. And it presses the rotating drum and hold it compressed and hold it tight so that the movement will not take place. So the band brake can be assumed as a flat belt where the transmission is zero, where the rotating drum is zero. So flat belt can be or the band brake can be assumed the model of the flat brake having zero velocity, that is the zero, it is transmitting zero force. So not transmitting zero force, actually it is not transmitting the motion, rather it is stopping the motion. Now if you consider the model of the flat belt, we know that for flat belt P1 by P2 is equals to E mu theta. P2 is given by E mu theta, where P1 is the tension on the tight side, P2 is the tension on the slack side or the loose side, and mu is the coefficient of friction lining between the brake drum and the steel strip. Theta is the wrap angle. You could see theta is the wrap angle. Now torque MT absorbed by the brake is given by, that is the total torque absorbed the brake for as the brake is moving. Now once the brake is becoming rest or do not from movement, it comes to rest. So that motion that is basically what the torque absorption by the brake is given by P1 minus P2 into R, is given by P1 minus P2 into R, where MT is the torque capacity of the brake and R is the radius of the brake drum, and R is this radius of the brake drum. Now force acting on the brake, and taking moments about the pivot. Now if you take about the moments about the pivot, then what are the moments? P2 into A and P into L. P2 into A, this moment, because P1 is taking as a pivot, so it will call zero moment. So the moment across the pivot, if you take P2 into A and P1 into L. So if we equate these two moments, P2 into A is equals to P into L, we get the value of the applied load P is equals to P2 into A by L. Now we are considering a very small elemental stripe. We are considering now for a very small elemental strip which makes an angle of R d phi, which makes an angle of d phi. So we take a very small strip of this brake. We take a very small strip from here. Suppose we take a very small strip from here, and I cannot show, and we shift this force for force analysis, we shift it over here, and we should see that what are the forces acting on this strip. Now we see that that stripe makes an angle of d phi. So if it makes an angle of d phi, so what happened, the area sustained it is given by R d phi, because we know AC is equals to R d theta. We know from this principle is that if this is S, this is R, and this is theta, so S is equals to R theta. From this we could calculate that the elemental area is equals to R d phi into width. Width is the width of the steel strip perpendicular to the board, that is in this direction, x, y and z direction. So this is the width. So this is the elemental area P into R d phi into omega. Now the reaction force Dn. Just if you multiply intensity of pressure acting on this with this area, we should get the value of the normal reaction Dn. So Dn is equals to P into A, and A is equals to R d phi into omega. Now what is P? Now here you could see P is a tension in the loose side, because if you see P, this is P2, so it corresponds to tension in the loose side, and P1 and P plus del P, this because this area is this small amount of area is del P, so P plus del P, that is the tension in the P plus del P is equal to tension in the tight side. Now if we go for an equilibrium analysis, of the strip, we could see that what are the forces acting over here. See, Dn is acting in the upward direction, so upward direction is taken as positive, so Dn is taken as positive, and this component, what are the component over here? This is P into cos d phi by 2, and this should be what? This component should be what? P into d phi by 2 into sin theta. Sorry, P into sin d phi by theta. P into sin d phi by theta. So this should be the downward component, and also this should P plus dP cos d phi by 2, and this should be P into dP sin d phi by 2. This is the downward component. So now if we put the value of the downward components, we will get dn plus upward direction, and the downward component is minus P sin d phi by 2, and another downward component minus P plus dP sin d phi by 2 is equals to 0. From this we get the value of dn. We get the value of dn is equals to P sin d phi by 2 plus P plus dP sin d phi by 2. From here, dn is equals to P into sin d phi by 2 plus P plus dP sin d phi by 2. When we just transfer this negative side on the right hand side of the equation. Now for small angles, as we know, for a very small angle, we know that the angle suspended is very small. So sin d phi can be assumed to be as d phi by 2. Sin d phi is assumed to be as d phi by 2. So if we put this over here, what we'll get? We get dn is equals to P d phi by 2 plus P d phi by 2 from here, plus dP into d phi by 2. Now this component is a very small, dP into d phi sin by 2, so we omit this component, this component. We basically omit this one because it is a very small component. So now the equation becomes T into P d phi, P into d phi. Now we know the value of this dn. What is this value of the dn? We have found out this value of dn as dn is equals to P into R d phi into omega. Now omega. Now if we put the value of this P over here, what we should get? We put the value of dn, and we put the value of over here on the denominator side. So we get this, where d phi and d phi cancels out, and ultimately we get the form P, so intensity of pressure P is equals to applied load by R into omega. Now P max, what is the maximum pressure? The maximum pressure should be when this applied load should be equals to P1. So when should be this P should be this equation, P is equal to P by R omega, when this P should be maximum. P should be maximum, that is intensity of pressure should be maximum when the applied load is equals to the load on the tight side. So P max is equals to P1 by R omega indicates the maximum pressure on the tight maximum pressure which can be taken by the brake when it is equal to the load, when it is equal to the force applied on the tight side, or the tension applied on the tight side. Now we are coming to the analysis of a differential band brake. Now we are coming to the analysis of a differential band brake. Now what is the function of a differential band brake? Why the differential band brake is used? The only requirement of differential band brake is the requirement for self-locking. Due to the requirement of self-locking, band brake is used. Now the construction of the band brake is shown. The steel strip is there and the rotating drum is there. Now one major difference is that not any one of a single side of the steel strip will pass through the pivot. Neither side, that is the tension side or the slack side or whatever, tension side or the slack side of the steel strip will not pass through the lever. So this is the main condition of the differential band brake. Now you show the differential band brake. This is the same principle. Where it will apply the condition of a brake, but the brake is not transmitting any force. So that is the condition. Now we do actually a free body diagram of the lever, free body analysis of the lever. Now we see that if this is the P1 side, this is the P1, this is the P1, that is I have told the tension side, P2 the slack side, and the distance of the P2 is A, and the distance of the P1 in that condition, as P1 is passing to the pivot, no distance is there. But over here, as I have told in the beginning, that there are the criteria of the differential band brake is that not a single side of the steel strip, either tension or the slack side, will pass through the pivot. So here it has got a distance B, and the application of force has got a distance L. Now for the self-locking criteria, first we should do the analysis. Moment analysis, equilibrium moment analysis for the fixed for the pivoted end O. So sigma MO. So sigma MO is given by minus P into L. What is the meaning of this? If you consider force from here, if you consider force from here, it will try to move the lever in this clockwise direction. So in this clockwise direction, is moment is always considered negative, normal convention. So it is taken as minus P into L. Now P2, that is the force acting on this side. So this side would try to cause the lever to move in the anti-clockwise. So see, if you consider the pivot, you will try to move the lever like this. So this becomes an anti-clockwise. So that is anti-clockwise moment is considered positive. So P2 into A, and again P, the force in the tight side, you will cause the lever, try to move the lever in this side, in the clockwise direction. So again it is negative, minus P2 into B, it will try to move the lever in this direction. So that is minus P2 into B. So if we equate this, we will get that P is equals to P2 into A minus P1 into B by L. Now we know that we are applying the belt consideration. So we know that P1 by P2 is equals to E mu theta for flat belt. Now if we put the value of P1 over there, and if we take that is, we transmitting all the components to P2 and we take a common, we get this form. P2 is equals to A minus B into E mu theta by L. So this is the form, this is the desired form. That is, the applied load P is equals to P2 into A minus B into E mu theta. So now what happens is basically that for self-locking condition, for self-locking criteria is that if you go for a self-locking criteria, what we could see that for that is P have to be 0, that is applied load have to be 0 or negative. That is possible only when A is less than equals to B into E minus B into E mu theta. So if A is less than equals to if you see this equation, if A is less than B into E mu theta, so what happened? This will become this load will become 0 or negative. So this load will either become 0 or negative. So this will either 0 or negative, I will become either 0 or negative. So this is the condition. So for this reason, what we should do is over here is that considering for self-locking, given that A by B have to be less than equals to E mu theta. So this is the criteria for self-locking. This is the criteria for self-locking, and these brakes are only required for self-locking conditions. Now this is all up. To differential band brakes, and the theoretical portion of the brakes, as far I have discussed, it ends up to over this up to this. Now we should be going to solve the problems afterwards in my next lecture. So if you like my lecture, really, if you put a thumb mark to it, and if you want to get more videos like this, educational videos or mechanical engineering related videos, just subscribe to my channel. Thank you. Have a good day.